Welcome to Module 10 of the Introduction to Chemistry. This week we're going to talk about method evaluation and quality management. This is going to be by far the most important part of your job as a medical laboratory technician. We need to make sure that every single lab test that we're sending out the door or result is accurate and that our quality control is within range so that we know it's accurate. So today I'm going to cover how we come up with these ranges and what quality control is. First, we'll start with a couple definitions here. We talk about quality assurance as kind of the big umbrella that encompasses all of the quality control. This ensures there's quality results and that the pre-analytical, analytical, and post-analytical stages of testing are all of top quality. The quality control refers to the actual analytical stage of doing testing. It's the process of monitoring results from control samples to verify quality patient results. I have three pictures of, three vials down in the bottom of the screen here. And that's just an example of what quality control might look like. So we run it just like we run patient samples, but each of those samples has a result that we should get. So for example, if we're going to be running glucoses on patients, we want to make sure that we run these controls and that we're getting the answers that are on these control vials when we run those glucoses. That means that our analyzer is working and giving the results that it should. If we're not getting the answers that we should get with each of these QC vials, then we cannot report patient results and we have to refer to the owner's manual or things like that with our analyzer to make sure that we can fix it to figure out why it's not coming in range. A couple other terms, sensitivity and specificity. With these, we want to make sure tests are sensitive. We want to be able to detect slight differences in concentration. Here's an example of sensitivity. So let's say you have a pregnancy test that picks up HCG, which is a pregnancy hormone. You want to have a test that's able to determine that a woman is pregnant very early on when those HCG levels are very low. That's having a good sensitivity. You don't want it to only pick up a positive result when that woman's 3 months pregnant. You want them to pick it up right away. Specificity is the ability of the method to determine the compound that it's supposed to measure. So let's talk about the pregnancy test again. So you want it to only pick up the fact that women are pregnant. You don't want any interfering diseases to come in and tell a woman she's pregnant even though she's not. So for example, this is off the wall, but let's say somebody had mono and it caused their pregnancy test to come up positive. Well, that is not good specificity. We want that test to only be specific for that HCG hormone. A few other ones, accuracy versus precision. Accuracy is how close you are to the true value. Precision is reproducibility. You get the same answer over and over and over, but you might not be accurate. And then we can have imprecision, which is a large amount of scatter. I got some pictures here. So here you can see we don't have accuracy or precision. This is me playing darts. I'm all over the place. Then you can have low accuracy but high precision. You can see the dots are very precise. They're all in the same spot, but they're not in the bullseye, so they're not accurate. I'm going to skip down to the one on the bottom right. We have high accuracy and high precision. That is where we would like to be. When we use quality control in the laboratory, we have a couple different types of things that we use. A standard and a calibrator, which sometimes can be interchanged. They have the same type of material to them. A standard is a solution that has a known amount of analyte. So if you open this vial of liquid, it'll say this has 100 milligrams per deciliter of glucose in it. A calibrator also has an assigned value, but with a calibrator, we use it to set standards on an analyzer. So we'll tell the analyzer, okay, this is what 100 looks like, this is what 200 looks like. So usually there may be a set of calibrators that we may use to set up an analyzer. A control is something that you're going to use most often. This is a sample that is chemically and physically similar to an unknown specimen and is tested in exactly the same manner. Remember the pictures that I showed you on the first slide of the 3 bottles? That would be an example of a control. Those are usually run every day, if not more often. We also look at statistics. Statistics is the science of gathering, analyzing, interpreting, and presenting data. Here are 3 tests that we do, and you're going to have to be familiar with these: mean, median, and mode. The mean is the average. You're going to add up all of the numbers and divide by the number of numbers that are there to give you the mean. The median is the middle. Okay, so you sort the numbers and you find the ones in the middle. The mode is the number that occurs most often. Next, we'll look at standard deviation. This is how we make our quality control graphs within the laboratory, so you're going to need to be familiar with how to do this process. We are going to do these in lab during week 10, so if this seems a little overwhelming for you right now, the examples that you're going to be doing in the classroom will definitely help you out. So the standard deviation refers to the spread of data around the average or the mean. It's the dispersion of data points. So this is what it looks like. We've got the square root of the sum of the mean minus, or the x minus the mean squared over n minus 1. Now x is what each number is. The mean has the x with the bar over the top. Little n is how many values you have. And that Greek e, looks like an e, is the sum across the values. So bear with me for a minute. I'm going to run through the steps. So here's how we find the results. I want you to keep these notes with you so that when you have to go and do it yourself, you can follow along. But I'm going to jump ahead and actually go through these steps with the actual numbers so it makes more sense. So here's our example. These are our results. Let's just say this is like an albumin. Okay, albumin results. Because that would be, well, that's grams per deciliter. Well, let's just pretend maybe creatinine. So we're looking at creatinine results here, and we ran it, let's see, 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so there's 11 answers here. That means n equals 11. That's how many times we ran the sample. When we add all of these together and divide by 11, we get a mean of 4. Our next step is to take 3.8 minus 4 to get negative 0.2. We then take 4.2 minus 4 to get 0.2. Okay, 3.8 minus 4 is minus 0.2. 4.5 minus 4 is 0.5. So all this column is each of these with the mean subtracted from it. Okay, which is what it's kind of saying here. Now up here there's a y instead of an x, but it's the same thing. Now we're going to take every single value in this second column and we're going to square it. Oops, sorry. So we're going to take 0.2, we square it, we get 0.04. Same thing with these. Notice when you square a negative number, you get a positive number. So we're going to go down and square every single one. And then when we're done with that third column, we're going to add that column together. Remember the crazy, thing that I just showed you? That was the Greek e and the mean minus, or the x minus the mean squared. All this refers to is the third column added together, and we get 0.98. All right, so now that we have the 0.98, as I showed you earlier, we divide by n minus 1. Remember n was 11? So that means we divide by 10. We divide by 10, we get 0.098. We take the square root of that, and we get 0.3. Therefore, one standard deviation is 0.3. 2 standard deviations is 0.6. 3 standard deviations is 0.9. When we look at standard deviations, we're looking at that whole group of numbers. So when I give you the group up here of these numbers, okay, you know the mean is 4, so that's kind of in the middle. So if we look at what's called a Gaussian curve here, 4 would actually be right in the middle. Okay, that's what this middle dotted line is referred to. All of those other numbers that we saw in that list would fit somewhere underneath this Gaussian curve. The majority of them, or 68.2 of them, would be between -1 and +1 standard deviation. When we looked at what our standard deviation was, it was 0.3. So what that means is -1 would be 3.7, +1 would be 4.3. the majority, or 68.2% of them, would fall between those. And I think if I jump back up to these numbers, you would agree. Between 3.7 and 4.3 is about 70% of those numbers. All right, then we have two standard deviations, which is 95.5%. We call this a 95.5% confidence interval. That is -2 to +2 standard deviations. 99.7% of all of the values will fall between -3 and +3. When we do quality control, we want our answers to fall between -2 and +2. We also have a coefficient of variation. This is used to compare data to determine which has great precision. In order to figure out if we have good precision, we take the standard deviation, divide it by the mean, and then we multiply that by 100. The lower the CV, the higher the precision. We'd like to stay less than 10. So here's what we would get with our previous example. Our standard deviation was 0.3. We divide by 4, and then we multiply by 100. The precision of this is 7.5%. This is good because remember, we want to be less than 10. If we set up our 95% confidence limit, okay, which is different from the coefficient of variation, plus or minus 2 standard deviations, it would be 3.4 to 4.6 milligrams per deciliter. Because the mean was 4. Minus 0.6 is 3.4, plus 0.6 is 4.6. Again, we're going to go through and do those in lab this week as well. So if that seemed to be a little overwhelming, make sure that you attend lab and go through it slowly with your lab instructor. Then when you come back and watch this again, you'll have those steps there for you. All right, so we have two types of quality control. We have assayed and unassayed. Majority of labs use an assayed control that comes with control ranges that we can use. An unassayed control is where the lab needs to establish its own control ranges. Next, we'll look at errors that we can encounter. We can have random or systematic errors. Random is an error affecting a particular determination that doesn't occur in a regular pattern. As you can see in the bottom right, we hit the bullseye, or hit the dartboard all over the place, very random. Systematic means there's something wrong with the system and you keep getting erroneous results over and over and over. Something like a systematic error, there may be something wrong with your analyzer, or you may need to recalibrate to get those results closer to the center. Random error is something that we see a little more often, with results all over the place depending on what is wrong with the patient. Next, we're going to look at how we plot this quality control on a chart. So what we've learned is what standard deviation, what do these numbers mean, what do they look like? This is where some of that's going to start to come together. This is a graphical representation of observed values of a control material over time. And when the values fall within those control limits, we're very happy. Okay? When they fall outside of control limits, problems are developing that need to be fixed. We cannot report patient results with poor QC. We can see random errors caused by variations in techniques and systematic errors that arise from factors that contribute to constant differences. So, this is a Levey-Jennings chart. Working in a medical laboratory, you're going to see many of these. A normal distribution curve lying on its side is what this is. So when we look at this, the green line going through the middle, looks like it's 250. That is the mean, okay? The green line's the mean. The yellow line is 2 standard deviations, and the red line is 3 standard deviations. There would be a 1 standard deviation right in the middle here. But we want to keep our QC between -2 and +2 standard deviations, okay? When we go out of that range, that's when we have to stop and not report our patient results. So you can see day 1, QC worked well, day 2 was good, 3 was good, 4 was good, 5 was good, 6 went out of range. So you run that QC every day. Once it goes out of range, we got to start thinking about what could possibly go wrong. Because it was only out one time, and we'll talk about these rules here in a minute, but when it's out one time between 2 and 3 standard deviations, we call that a warning. And you run it again, and if it's in range, you're good to go. It went up here, it did it again, so we're still good to go because it only went out one time again. Day 9 is good, day 10 is good. Oh, day 11 was above 2 standard deviations, ran it again, we were okay. All right. Now where things become a problem is on day 13, we had a -2 standard deviations. That's out of range, right? We want to be in between those yellow lines. The first time's okay. You just kind of keep an eye on it. The second time is bad. Once it's out 2 times beyond 2 standard deviations, but within 3, we have to figure out what's wrong with the analyzer. We cannot report patient results. It looks like something was done here. Maybe they took out some fresh vials of controls. Maybe they, did something to the analyzer to help it out, and it became back within range. We like to see a really nice smattering about the mean here. Back and forth, back and forth. We don't want to see them all on one side. So the control limits are those numerical limits within the values of controls that they must fall in for the assay to be considered valid. Most labs use +2 to -2 standard deviations. Next, we'll look at outliers, shifts, and trends. An outlier is a crazy result. You have to investigate it, but let's say it just totally jumps off the charts. I don't have a picture of this, but let's say you're happy going along on your Levey-Jennings chart. All of a sudden, one jumps way up above 3 standard deviations. What happened? Did you suck up a bubble? Is there a clot? There's lots of things that could possibly cause that, but you have to look into it. Then we have shifts and trends. Shifts are very sudden, and trends are gradual. I got pictures of this one for you. So you can see A goes back and forth, okay, which is what we want to see. We want to see it go back and forth. But then B, we have the mean, and you can see, it's starting to trend upwards until we're almost completely out of range. This can happen once QC starts to get old. I mean, the shelf life doesn't last forever. They do have expiration dates. So as the QC starts to get yucky, okay, or the reagents and chemicals we're using get old, you can see it trends out. Now down here we have a shift. So everything's going along well, and all of a sudden, boop, drops down and it stays there. That is a shift. Something happened, probably to the analyzer, that caused it to have all the results shift out of range at once. There could be a clogged probe. There could be something else, an electrical glitch or something that happened. Or somebody could have changed reagents without telling you, without running any calibrations. So here are the quality control, what we call Westgard rules that we follow. 1-2S, and I'm going to flip back and forth here to kind of show you the examples. 1-2S is where one control exceeds the mean, and it's a warning rule. So that is what I showed you up here. These guys are 1-2S. Okay, this is a 2-2S down here. That's what we're going to talk about next. Okay, 1-3S would be where it goes over 3 standard deviations. Rejection, you can't keep going. You have to stop and see what's wrong. 2-2S was the second one that I showed you that had 2 of them between 2 and 3 standard deviations. We can have an R4S, which is where the difference between 2 controls is greater than 4 standard deviations. We have a 4-1S, okay, that's where 4 consecutive controls exceed the mean by 1 standard deviation. So that would be, you would have 4 of them up here or 4 of them down here. Okay, you can't have that. And finally, 10X. If you have 10 controls on one side of the mean, that's a rejection as well. So what's important to know is that everything but having 1 out just over 2S is a rejection. You cannot keep reporting patient results if your QC fails. So some things that we need to look at when we're interpreting our quality control. We look at all levels of the control ran and see if there are any out 2 standard deviations. If not, good to go. Accept those results and continue on. Yes, determine what Westgard rule was violated and figure out what to do. Is only one level of control outside 2 standard deviations? Well, maybe there's something wrong with the QC then. You just take out a new bottle. Is the control out 2 standard deviations or 3 standard deviations? Have the controls been falling on one side of the mean? If only one control, is out 2 standard deviations, was the prior control acceptable? So we have to go and look at those and figure out what we're going to do next. If we need new QC, do we need new reagent, or is there something on the analyzer that needs to be fixed? Here are some general approaches to out-of-range QC. We can repeat the control, which is the first thing that you usually do. to see if there's a human error, right? We can run a new vial, which is what you might want to do next to see if it's been outdated, improperly stored, or contaminated. We can run a control from a different lot if the old lot is, maybe too old. We can perform maintenance, check reagents, or rerun the control. We can recalibrate and rerun the control. We can call. That's the best part, is there's always a 1-800 number on your analyzer to fix it. And we need to document anything that we've done. A couple other QC tools that we use that are very important are, one of them is the delta check. This is the most recent result of where the patient is compared to the previous one. So let's say a diabetic, is admitted to the hospital and they have a glucose of 500, okay, just really high. And then they treat the patient with a bunch of insulin, and the next result is, let's say they gave them too much insulin, the next result is like 40. Well, this would show as a delta check on our analyzer in our computer system. You would get a flag that pops up that says, you might want to check this because the patient was 500, now it's 40. Well, if you look in their chart and you can see, oh, they just had insulin, that makes sense. They were given a lot of it. Well, then you can go ahead and approve that result. What could have happened is, if you went from 500 to 40, what if there was a patient that was, they mislabeled? Okay. What if there's something wrong with the analyzer? What if, there's all different what ifs that could happen. So we need to look into it and make sure that it makes sense. You can't just say, oh, it's 500, now it's 40, and report it. Those delta checks mean there was a pretty severe change, and you need to figure out why and make sure it makes sense. The next thing is proficiency testing. This is required by all labs that perform moderately complex or highly complex testing. So what they do is they send you a little vial. You can see this guy here with this little vial, and it'll have some numbers on it, and it comes in the mail. And we have to run it just like we run a patient. So let's say we're doing glucoses in our lab. The state lab, or even national, labs, depending on what type of certification they're signed up for, will send them these samples. They'll run it on their analyzer just like they'd run a patient. They write down the results and they send it back. The results better be accurate. Okay, so they're checking to make sure that you are doing testing that is accurate and is in the best interest of the patient. So that is how proficiency testing works. All right, that concludes our final chapter on quality control. So like I said, if this seems a little overwhelming, we're going to do these things in lab, and then you're going to have some homework that goes over it as well. So this will completely help you out.